Hello and welcome to this presentation relating to solving first order differential equations of the form dy by dx is equal to a function of y. This is the second presentation in the series. The first presentation solved differential equations of the form dy by dx is equal to a function of x. It strongly encouraged you review the previous presentation before reviewing this presentation. Here's a brief overview of this presentation. We commence with some background and reference information to be aware of. We also list standard integrals and differential tables, along with the laws of logarithms and the laws and the rules of indices. Next is example 2. This is a fully worked example where we solve the first order differential equation 6 times dy by dx is equal to 3y minus 5. We then have exercise 2, which contains 4 separate parts. Firstly, we solve the differential equation dy by dx is equal to 3 plus y. The second part of exercise 2, we solve the equation 3 times dy by dx is equal to sec of 2y. We're also given an initial condition, x is equal to 1, y is equal to 3 pi divided by 4. Part 3, we solve the equation half times y times dy by dx is equal to 4y squared plus 3. And finally, part 4 is a descriptive question where we're given a first order differential equation in terms of theta in t this time, and we have to solve the equation for theta, again given initial condition t is equal to 0 and theta is equal to theta naught. And here are the approximate start times related to the various items as shown on this slide. There are some questions included at the very end of the presentation for your reference, but please note all times are generally rounded to the nearest minute. Here's some background information. As stated previously, it's strongly encouraged you review the previous presentation related to solving first order differential equations of the form dy by dx is equal to a function of x. The integrals were solved using standard form, but within this presentation we will also need to apply the integration using substitution method. This method we reviewed in a previous presentation, and also within the substitution method we will have to differentiate using standard forms and tables. Within some questions we will also have to make use of the laws of logarithms and the laws and the rules of indices, and also be aware of our trigonometric functions. We're quite familiar with sine, cosine and tangent, but we also need to be aware of their reciprocal functions, cosecant, secant and cotangent, often referred to as cosec, sec and cot respectively. Some reference information here. This is a table of standard integrals. We'll be referring to some of these throughout the presentation. Just notice here the format used sometimes confuses students. If you consider the integrand cos ax, it integrates to 1 upon a multiplied by the sine ax plus c. But note that's the same as sine ax divided by a plus our constant of integration c. The fraction sometimes confuses some students. Same with the integrand sine ax, that integrates to negative 1 upon a multiplied by cos ax plus c. But that could be written as negative cos ax divided by a plus c. There's a reference information here, the laws of logarithms, first, second and third law stated here, the laws and the rules of indices stated on the right hand side, and also various trigonometric ratios. Definition of tan theta is sine theta divided by cos theta. Cosecant theta or cosec theta is the reciprocal of sine theta. Secant theta or sec theta is the reciprocal of the cos theta. And cotangent theta or cot theta is reciprocal of tan theta. We'll be referring to some of these ratios within the following problems. And here's also our standard derivative table. Again, we refer to this within some of these solutions. So as mentioned before, we're considering these first order differential equations. There are actually 3 types to consider, but within this presentation we're considering equations of the form dy by dx is equal to a function of y. As stated in the previous presentation, all these forms of differential equation can be solved using the integration process. we will find that within each question it's possible to separate the y terms onto one side of the equation and the x terms on the other. Solving these types of differential equations using direct integration is termed separating the variables. A variable is separable. So the solution to differential equations is the form dy by dx is equal to a function of y. We will find that an equation stated in this initial form, dy by dx equals a function of y, is initially rearranged to give the format dx is equal to dy divided by the function of y, from where we can then solve by direct integration. In this presentation, all our integrals will be rearranged into this format. Let's consider example 2, fully worked through for us here. We're asked to solve the differential equation 6 times dy by dx is equal to 3y minus 5. Here's the commencement of the solution. So given the stated problem, we're going to rearrange to have all the y terms on one side of the equation and the x terms on the other. So to rearrange, I multiply both sides throughout by dx and divide both sides throughout by 3y minus 5. So I can write this down now as dx is equal to 6 divided by 3y minus 5, and that's all multiplied by dy. On the next line, I've simply brought the 3y minus 5 in the bracket to the top line. Notice I've made the bracket now to the power of -1, just a reformatting of the previous line. Now that's a non-standard integral. You won't see that in our integral tables. We'll be looking for an integrand of the form 1 divided by ax plus b, that kind of generic format, but we don't see that in our tables. This is considered a non-standard integral. By applying integration using substitution, this technique we reviewed in a previous presentation, essentially we make a substitution into the right-hand side of the equation shown here. Substitution is usually for u, so let u is equal to, in this case, u is equal to 3y minus 5. And what we have to do now is replace all the y terms with u terms. So the bracket will be replaced with u, but we also need to replace the dy with du. To find du, we have to differentiate this equation. So differentiating the left-hand side with respect to y, we have du by dy. Differentiating the right-hand side, now remember we're differentiating here. Referring back to our differential tables, we'll be using this format, ax to the n, which differentiates to anx to the n minus 1. So please note we're differentiating within the integration process. That sometimes does confuse students. So when we differentiate the right-hand side, differentiating 3y with respect to y becomes 3, and differentiating a constant, that always disappears. And again, let's assume you're familiar with the differentiation process covered in our previous presentations. So that dy is equal to du divided by 3. So now we simply replace the bracket of 3y minus 5 to the power of -1 with u to the power of -1, and we replace the dy with du divided by 3. On the next line, I've simply divided the 6 by 3 to give us 2 here. So we have 2u to the -1 multiplied by du. That's still equal to dx on the left-hand side. So now we actually have a standard form, because integrating u to the -1 with respect to u is essentially item 2 in our tables, the 1 upon x, or x is -1. When we integrate this function, it becomes ln x plus c. So we basically have 1 upon u, or u to the -1, so our solution will integrate to ln u plus c. Example 2, solution continued. So now essentially on the left-hand side, integrating of 1 with respect to x, standard form will become x. On the right-hand side, we have the integral of u to the -1 with respect to u. That's our standard form. That will integrate to ln u plus c. And because we have a 2 outside the integral, we simply factor the ln function by 2. Finally, back substituting for u, now basically substituting the u with the 3y minus 5, we have our full solution that x is equal to 2 times ln of 3y minus 5 plus the constant integration c. So that's the general solution for example 2. Here's example 2 solution continued. Just repeated this line from the previous slide for convenience. What we're going to do now is manipulate this general solution into another form. In fact, the form shown here at the bottom of the slide. And this is because some questions will state the final format of the solution required. And it does need some manipulation. So I'm just going to show you sort of some tips and wrinkles here, essentially as how we can manipulate the 2ln 3y minus 5 plus c equation into that shown at the bottom of the slide. So what we need to be aware of here is that we added a plus c to our equation when we integrated. That's the constant integration we always add when we're solving indefinite integrals. But we could have quite easily called constant c ln k, which is just another constant. And the reason why I'm choosing to replace c with ln k here is because in this final solution at the bottom of the page there is only one log function, so somehow they've brought together the c and the ln function into one function. By stating c as ln k, this will now be achievable. So on the next line I've replaced the plus c in the above equation with plus ln k, and also now I've applied the third law of logarithm to the log function. Instead of having 2 times ln 3y minus 5, notice I have ln 3y minus 5, but now raised to the power of 2, which is just applying the third law of logarithms shown here. Now we have two ln functions that are added together, so by applying the first law of logarithms, we can actually bring these two log functions into one function. So I said this is the first law of logarithms applied to the right hand side. So essentially we have ln of k multiplied by the 3y minus 5 raised to the power of 2. So that's our final solution for x in this case. So the last few lines are really nothing to do with the integration process here. They're just algebraically manipulating the general solution we found from our integration process into another form. And I said sometimes these additional forms are stated within the question. And for your reference, here's example 2. We work with a slightly different solution. This essentially is an alternative solution using standard form. So in the previous solution, we used integration using substitution. Here I'm actually going to use a standard form, and this standard form is shown here. The function dash x divided by function of x can be written as ln of the magnitude of the function of x plus c. So if we refer back to this line of our solution we had on a previous slide, dx is equal to 6 divided by 3y minus 5 multiplied by dy here. The standard form on the right hand side assumes that the numerator is the first differential of the denominator, thus the f dash x is the first differential of the fx. If we have that situation, we could simply write the solution down as the ln of the magnitude of the function of x plus c. In this case, we actually have 6 divided by 3y minus 5. If we differentiate the 3y minus 5, and don't forget we're differentiating here with respect to y, we would have 3. Now if we had 3 on the top line, we would comply with the above standard integral. So we could write this fraction as 2 times 3 divided by 3y minus 5. Now we have the standard form, the numerator on the top line here, 3, is the differential of the denominator, the bottom line here, but we need to factor it by 2. So to make it standard form, my integral has to be written like this: 3 divided by 3y minus 5, integrating with respect to y, will produce the standard solution of ln 3y minus 5, but we will need to now factor it by the 2. The rest of the solution to find the final form is the same as we looked at on the previous slide, but it's just this integration process that now uses standard form that can slightly speed up the solution process. If it's of benefit to you, I've actually written example 2 alternative solution using the standard form here and tried to show in greater detail how we take our original integral and now make it into a standard form that we can just simply write down the solution. Not sure if that helps you with your understanding. I just tried to add further clarity to the process of using the standard form. So here's exercise 2. We're asked to solve the following problems, which are all in the form of dy by dx is equal to a function of y. So essentially we're going to use the process outlined in example 2 to solve the 4 problems shown here in exercise 2. If If you think you can attempt any of these questions without further assistance, I'd encourage you to stop the presentation and do so. The answer to each of these problems is shown in the right-hand side square brackets for your reference. Question 4 is just a descriptive question. It looks more complicated, but it's the same process involved as in all the questions. On the following slides, I will now outline the full work solutions to each of the problems shown in exercise 2. Use exercise 2, part 1, we're asked to solve differential equation dy by dx is equal to 3 plus y. Notice 2 answers are given here for this particular problem. Just notice a minor point, sometimes I show ln written as a capital Ln and sometimes with lowercase ln. That's just my slight inconsistency. The general convention is to use lowercase ln. If you think you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now, but the full work solution will be shown on the following slides. So here's exercise 2, part 1. We're asked to solve dy by dx is equal to 3 plus y. So I just stated the equation here, single line formatting. So again, rearranging the equation, multiply both sides by dx, divide both sides by 3 plus y. Just turn the equation around here, so I have dx on the left-hand side. So dx is equal to dy divided by 3 plus y. What I've done on the next line is simply brought the bracket to the top line. We're dividing by 3 plus y here, so I can write that as 3 plus y to the power of negative 1. As for example 2, this is a non-standard form, so I'm initially going to use substitution to help solve this problem. That u is equal to 3 plus y, differentiating du by dy is equal to 1. Differentiating 3 with respect to y, it disappears. Differentiating y with respect to y becomes 1. So we can clearly see dy is equal to du. So we can now write our integral on the right hand side as u to the negative 1 multiplied by du. And of course that's still equal to dx. We'll undertake the integration process on the next slide. Part 1, solution continued. Just repeated this line from the previous slide purely for convenience. On the left hand side now we integrate 1 with respect to x. On the right hand side we integrate u to negative 1 with respect to u. On the left hand side that becomes x. On the right hand side that becomes ln u plus c. The left hand expression is in the form ax to the n. It integrates to ax to the n plus 1 over n plus 1 plus c. And the right hand side is of the form 1 upon x, or x to the negative 1, that integrates to ln x plus c. Of course we only need to add 1c onto one side of the equation. And then we back substitute for u. U was 3 plus y, so we have now ln 3 plus y plus c on the right hand side is equal to x on the left hand side. So as I say, there are 2 solutions given in the question. This one we found already, and this one we have to now try and prove. So as for the solution shown in example 2, here we're going to let the constant c equal another constant ln k. So replacing c in this line with ln k in this line. And then we can simply apply the first law of logarithms, shown here, to write our final solution. So x is equal to ln the bracket of k multiplied by 3 plus y. Exercise 2i. Again, this shows a more detailed slide relating to the alternative of using the standard form for the integration process. So considering the integral of 1 dy divided by 3 plus y, if you differentiate the left hand side denominator, differentiating 3 plus y with respect to y, it's a value of 1, and we actually have 1 in the numerator. So in this case, the numerator is the first differential of the denominator. So we simply apply the standard form as written, that integrating 1 divided by 3 plus y with respect to y integrates to ln of 3 plus y. Here the right hand side simply integrates 1 with respect to x, so that's x plus c. Added the c to the right hand side here. Here's exercise 2, part 2. We're asked to solve 3 dy by dx is equal to sec of 2y, given that x is equal to 1 and y is equal to 3 pi divided by 4. I would encourage you to stop the presentation and attempt exercise 2, part 2, but the full work solution is shown on the following slides. So here's exercise 2, part 2, commencement of the solution. So given the first order differential equation, which I've written here, notice from our previous tables that sec theta is actually the reciprocal of cos theta, referring back to our reference information. Here sec theta is equal to 1 upon cos theta. So we can rewrite the right hand side of our equation. Instead of sec 2y, it's 1 upon cos 2y. Now rearranging on the next line, I multiply both sides by dx, and I multiply both sides by cos 2y. So writing dx on the left hand side of the equation, in this case that's equal to 3 cos 2y dy. Both the left hand and right hand expressions are in standard form. The left hand side is essentially ax to the n format, integrating 1 with respect to x. And the right hand side is in the cos ax format. I've placed the 3 outside the integral, so our integral is of cos 2y with respect to y, and that's the standard form of cos ax integrated with respect to x. So left hand, so integrating 1 with respect to x becomes x, and integrating cos 2y with respect to y, we can see becomes sine 2y upon 2, plus the constant integration. So that's our right hand side of the equation, and of course we're factoring the integral by 3 here. So that's the general solution for exercise 2 part 2. Exercise 2 part 2 solution continued. Just repeated this line from the previous slide for reference. Now we're asked to find the particular solution. We're given that x is equal to 1 and y is equal to 3 pi divided by 4 radians. Inserting the x on the left hand side, the y on the right hand side. We can evaluate c. I'll let you review the calculations at your own pace. Just make sure your calculator is in radians mode if you're typing sine of 3 pi divided by 2 into the calculator. So that's your value of -1. And purely for your reference, here's the sine wave plotted between 0 and 2 pi radians, and we can see at 3 pi upon 2 radians, or 1.5 pi, the ratio is -1. So we find that constant c is 5 divided by 2. So our final solution for exercise 2 part 2, x is equal to 3 multiplied by the sine of 2y divided by 2 plus 5 upon 2. And the last line just slightly simplified the right hand side, because 3 divided by 2 of course is 1.5. So 1.5 multiplied by the sine of 2y plus 2.5, 5 divided by 2. That's the full work solution for exercise 2 part 2. Exercise 2 part 3, we're asked to solve a half of y multiplied by dy by dx is equal to 4y squared plus 3. If you can attempt this question without further assistance, I would encourage you to stop the presentation and do so now, but the full work solution is shown on the following slide. So here's exercise 2 part 3, commencement of the solution. Just written the equation here on one line. Again, rearranging for x onto one side and y on the other, I multiply throughout by dx and divide throughout by 4y squared plus 3. So again, writing dx on the left hand side is equal to a half y dy divided by 4y squared plus 3. What I've done on the next line is simply brought the denominator of 4y squared plus 3 to the top line and raised the bracket to the power of -1. This is a non-standard form. Initially I'm going to use substitution to solve this integral. So using substitution, I'll let u equal to the 4y squared plus 3 in the bracket. Differentiate u with respect to y, equal to 8y here. So rearranging dy is equal to du divided by 8y. So inserting u into a above equation for the bracket, I get u to the -1, and replacing dy in terms of u, that's du divided by 8y. What we notice now is the y in the numerator, the top line, cancels with the y in the denominator, the bottom line. So I notice that I got half multiplied by 1 upon 8 here. The 8 is in the denominator. Not so easy to see when it's written on one line, but it's basically a half multiplied by an eighth. That gives us 1 upon 16 multiplied by u to the -1 multiplied by du. And if it helps for clarity, I've tried to show the expression here in two-line formatting. So hopefully you can clearly see the y in the numerator cancels with the y in the denominator, and you can see that in the denominator we have 2 multiplied by 8 to give us a 16. So now we're ready to perform our integration. The left hand and right hand side are now standard forms. So exercise 2, part 3, solution continued. Just repeated this line from the previous slide. So here's our integral on the left hand side. We're integrating 1 respect to x. On the right hand side I've taken the 1 upon 16 outside of the integral sign. So we're actually integrating u to negative 1 respect to u. The left hand expression is in the form ax to the n. It integrates to ax to the n plus 1 over n plus 1 plus c. And the right hand side is of the form 1 upon x, or x to negative 1. That integrates to ln x plus c. So our next line we have x is equal to 1 upon 16 multiplied by ln u plus c. And now we simply back substitute u on the previous slide stated as equal to 4y squared plus 3. So we now have x is equal to 1 upon 16 multiplied by ln of 4y plus 3 in a bracket plus the constant of integration c. Exercise 2, part 3, solution continued. Just repeated this line from the previous slide, and again as in previous solutions, we have to manipulate this equation into the final form required. This is shown at the bottom of the slide here, stated in the original question. So to progress the solution, we now replace the constant c with ln k, which is just another constant. So that's shown here. I've also in this line applied the third law of logarithms. So instead of multiplying the log function by 1/16, I'm now raising the log function to the power of 1/16. That's the third law applied. And on the next line I apply the first law of logarithms. So we're adding the ln functions together here. But using the first law of logarithms, we can write now as ln of our bracketed term raised to the power of 1/16 multiplied by k. What has happened on the last line, I just reordering inside the bracket. So now we have ln of k multiplied by our bracket raised to the power of 1 upon 16, which is the answer we're trying to obtain. So that's the solution to exercise 2, part 3. However, I will show you this solution for exercise 2, part 3. It's essentially an alternative solution using the standard form of function dash x divided by function of x integrates to ln of function of x plus c. The question essentially commences in the same way as before, so I've rearranged to get the x's onto one side and the y's on the other, but in this solution I've actually multiplied throughout by 2 to remove the half. So when we rearrange this time, we'll have 2 dx on the left hand side and y dy divided by 4y squared plus 3 on the right hand side. Just slightly reorganize the right hand side here. So using this standard form, if the numerator is the first differential of the denominator, we can write our solution down as the natural log of the denominator plus c. But when we differentiate the denominator of 4y squared plus 3, we actually end up with 8y. On the top we have 1y. So we need to factor the numerator by 8 to make it into standard form. But of course we'll also have to have an 8 outside the integral to prevent changing the original question. So integrating on the left hand side is all standard form, integral of 2 dx. Integrating on the right hand side, integral of y divided by 4y squared plus 3 with respect to y. And so we can make it standard form by having 8 in the numerator, but that means we have to multiply this solution by 1 upon 8 to not affect the overall problem. So on the right hand side we have 1 upon 8 multiplied by the ln of 4y squared plus 3. Here's exercise 2, part 3, our alternative solution using the standard form continued. I just like to show in greater detail how the right hand integral has to be rearranged to make it into standard form, shown here. So in this integral at the bottom of the slide we now have standard form, because when we differentiate the denominator, function of x, we get 8y, and that is the numerator, 8y in this case. but of course we've had to then factor the integral by 1 upon 8. So write down our solution is ln function of x, so ln the denominator here, but we're multiplying by 1/8. Add my c to the right hand side here. The left hand side of course is all standard integration. Integrating 2 respect to x becomes 2x. I'll let you review this slide at your own pace. So integrating 2 respect to x on the left hand side we have 2x, and I've added the constant integration on the left hand side here. Exercise 2 part 3, alternative solution, continued. Just repeated this line for convenience from the previous slide. Again we have to manipulate the equation into the final form, shown at the bottom of the slide here. So we'll be introducing another constant by letting c is equal to ln of e in this case. Ln of e is just another constant. Slightly more lengthy process here than in the previous exercise 2 part 3 solution, essentially applying the various laws of logarithms and indices. I'll let you review the solution at your own pace. Just notice we have yet another constant here. We're letting 1 upon e to the power of a half equals to capital K. It's just another constant. And this is all in the purpose of trying to find the final solution for x, as stated here. If you find this particular part of the solution difficult to follow, you won't be alone. Most technician engineering students do find the application of the laws of logs and indices quite problematic. So just an alternative solution to that shown previously. Here's exercise 2 part 4. This is a descriptive question. It says the rate at which a body cools is given by the equation of d theta divided by dt is equal to negative k theta, where theta is a temperature of the body above its surroundings and k is a constant. We're asked to solve the equation for theta given that t is equal to 0 and theta equals to theta naught. Here's the answer shown in the square bracket. If you think you can attempt exercise 2 part 4 without further assistance, I would encourage you to stop the presentation and do so. The full work solution is shown on the following slides. So here's exercise 2 part 4, commencement of the solution. We're given a question that d theta divided by dt is equal to negative k theta. So we do not have x and y in this particular question, but t and theta. So again I'm going to rearrange the equation to get t on one side and theta on the other. So multiplying both sides by dt and dividing both sides by negative k theta. I've written here on the left hand side dt is equal to d theta divided by negative k theta. On the next line I've simply brought the theta from the bottom line to the top line, so theta is negative 1 d theta divided by negative k, and again just slightly rewriting on the next line, dt is equal to negative 1 divided by k multiplied by theta to negative 1 d theta. Now both the left hand and right hand expressions are in standard form. The left hand expression is in the form ax to the n. It integrates to ax to the n plus 1 over n plus 1 plus c. And the right hand side is of the form 1 upon x, or x to the negative 1, that integrates to ln x plus c. So using the standard tables, we can now integrate the left hand and right hand sides of the equation. Exercise 2 part 4, solution continued. Just repeated this line for convenience from the previous slide. So on the left hand side, integrating 1 with respect to t becomes t. On the right hand side, integrating theta to negative 1 with respect to theta, that becomes ln theta, which of course is factored by the negative 1 divided by k. And in this case I've added the c to the right hand side of the equation. And I've actually called it c1 here. On the next line I've used the third law of logarithms, shown here, on the right hand side of the equation. So instead in the previous line of multiplying by negative 1 upon k, using the third law of logs, ln theta to the power of negative 1 upon k. And we're given in the question the initial condition that when t is equal to 0, theta is equal to theta naught. So imposing the value of 0 for t and theta naught for theta, I can find that my constant C1 in this case is negative ln theta naught to the power of negative 1 upon k. Exercise 2, part 4, solution continued. Just repeated this line from the previous slide. Reference. We can now state our particular solution by including now the constant C1 we evaluated on the previous slide, this term shown here, and applying the second law of logarithms to the right hand side. We can write t is equal to the natural log function ln as theta to the power of negative 1 upon k divided by theta naught to the power of negative 1 upon k. Exercise 2, part 4, solution continued. Just repeated this line from the previous slide for convenience. So next we're going to apply antinatural logarithms, that's basically the exponential function, to both sides of the equation. So exponentializing the left hand side we have e to the power of t, exponentializing the right hand side, the e cancels with the ln to leave us with theta to the negative 1 upon k divided by theta naught to the negative 1 upon k. On the next line I simply multiplied throughout by theta naught to the negative 1 upon k. I'll just turn the equation around here. So I have theta to the negative 1 upon k is equal to theta naught to the negative 1 upon k multiplied by e to the power of t. On the next line I'm actually inverting both sides. So inverting the left hand side, we move from theta to the negative 1 upon k to theta to the 1 upon k. On the right hand side we move from theta naught to the negative 1 upon k to theta naught to the 1 upon k. And we move from e to the t to e to the negative t. That's essentially inverting both sides of the equation. Finally, we raise both sides of the equation to the power of k. So on the left hand side we have theta to the power of 1, which is simply theta. On the right hand side we have the bracket raised to the power of k. So our solution for theta is equal to theta naught to the power of 1, or simply theta naught, multiplied by e to the power of negative kt. We've used the third law of indices here on the right hand side to obtain the final result. And that's what we were asked to prove in the question, as stated here. Here's exercise 2, part 4, solution continued. Here's an alternative approach to the solution. The only thing that's different on this slide is that for the general solution, I've added C2 to the left-hand side of the equation, shown here. In the previous solution, I showed that C1 was added to the right-hand side. All I'm trying to show here is it doesn't actually matter which side of the equation you add the constant of integration. You'll ultimately get the same answer. Here the C2 is evaluated to be ln of theta naught to the power of negative 1 upon k. With our original solution, C1 equal to negative ln theta naught to the power of negative 1 upon k. So we have a sign change on the ln function depending on which side of the equation we state the constant of integration. Exercise 2, part 4, alternative solution continued here. But if we show the development from the general solution through to the particular solution, although the constant of integration has a different sign, the final solution for t will be identical. So this is the particular solution, the constant C2 on the left hand side, and here's the particular solution with constant C1 added to the right hand side. As you can see, they're exactly the same solution. So as I say, it doesn't matter which side you add the constant of integration, you end up with the same solution. And finally, I'll leave you with some tutorial questions for you to attempt at your own pace. They all relate to first order differential equations of the form dy by dx is equal to function of y. So here's question 15 through to question 19. They'll all be able to be rearranged so that the x terms are on one side of the equation, the y on the other. Just notice in question 16, we have a cot function. If we refer back to our trig ratios, notice that cot theta is the reciprocal of tan theta? Answer to question 15, 16, etc. through to 19, shown in these square brackets on the right hand side. Notice question 15 to 19 result in general solutions. In other words, there's a constant of integration within our solutions on the right hand side. Tutorial questions continued. Question 20, question 21, question 22. Again, answers are shown in these square brackets on the right hand side. Just note with these three questions we are given initial conditions to consider, which means we'll be able to evaluate the constant of integration. In other words, there's no constant integration in these final solutions. And tutorial questions continued. Question 23 and question 24 are descriptive questions, but essentially the same approach is applied to all questions. Here's the bibliography used to help generate this presentation, a very good technician engineering textbook. I hope this presentation has been of use to you, and as always, thank you for viewing.